Right now, in our own solar system, on the largest planet we have ever known, something is happening that not a single scientist on Earth can fully explain. A storm the size of 1.5 Earths, raging for nearly 400 years, and instead of dying like everyone predicted, it is getting stronger. Tonight we go deep into Jupiter's atmosphere, past its swirling clouds and crashing winds, into a mystery that is reshaping everything we thought we understood about planets. If you enjoy what we uncover tonight, go ahead and like and subscribe. We are just getting started. Take a breath. We launch into the deep. For over a century, scientists had a simple prediction about Jupiter's most famous feature, the Great Red Spot, that enormous swirling storm, visible even through backyard telescopes, was supposed to be dying. The math made sense. The storm had been shrinking. Back in the 1800s, it was wide enough to fit 3 Earths side by side. By the time modern telescopes got a close look, it had dropped to just over 1 Earth in width. The trend was clear. Scientists measured it, modelled it, and concluded the obvious. This ancient storm was running out of energy. Give it enough time, and it would simply fade away. Then something happened that no one expected. The storm stopped following the rules. Instead of continuing to weaken, instead of slowing down and fading like every model predicted, the Great Red Spot began to change in a completely different direction. The winds at its outer edges, already moving faster than anything on Earth, started accelerating. Not dramatically, not all at once, slowly, quietly, in a way that did not show up until scientists went back and analysed years of data from the Hubble Space Telescope. What they found left the research community genuinely unsettled. The winds at the edge of the storm were picking up speed at roughly 1.5 miles per hour every single year. That sounds like almost nothing, and on Earth, it would be. But we are not on Earth. We are looking at a storm where the outer winds already reach 400 miles per hour. That is more than twice the speed of the most violent hurricane ever recorded on our planet. A storm that wide, spinning that fast, accelerating even slightly, that is not a small discovery. That is a system building power while everyone was waiting for it to collapse. Think about what that means for a moment. Every scientific model, every projection, every paper written about the red spot's future was pointing in one direction. The data said otherwise. And in science, when data contradicts the model loses. Researchers had to go back to square one. Something was feeding this storm. Something was pumping energy into a system that should have been running out. And despite everything we have sent to Jupiter, despite the orbiters and the probes and the decades of observation, that something remains unidentified. The question that every researcher is now sitting with is the same one that will follow us through this entire journey. What is feeding it? Nobody knows. And that is exactly what makes what comes next so unsettling. The models said the storm was dying. The data said it was not. And in that gap between what was predicted and what was actually happening, a new and stranger story began to take shape. Something was keeping this storm alive. Something was making it stronger. And figuring out what that something is has become one of the most important unsolved problems in planetary science today. Forget numbers for a moment. Let us make this real. The fastest wind speed ever measured in a tornado on Earth was 201 miles per hour. That was enough to rip houses off their foundations, throw cars through the air, and level entire neighborhoods in seconds. Emergency sirens go off. People evacuate. Governments declare states of disaster. That tornado lasted a few minutes and carved a path of destruction that made international news. The winds at the edge of Jupiter's Great Red Spot are moving at 400 miles per hour. Double that tornado, double the force, double the destruction, and it does not last a few minutes like a tornado does. It has been spinning continuously for longer than the United States has existed as a country. Now, Imagine standing somewhere near that outer edge. You would not be able to breathe, obviously. But forget that for a second. At 400 miles per hour, the air itself becomes a weapon. Every tiny particle, every fragment of ammonia crystal, every molecule of gas moving at that velocity hits with the force of a bullet. You would not simply be blown away, you would be torn apart before you could register what was happening. At the center of the storm, interestingly, it is a completely different story. The core of the Great Red Spot is surprisingly calm relative to its edges. Winds there move much more slowly. The storm is structured almost like a spinning donut, violent and extreme at the ring, strangely quieter in the middle. Scientists call this kind of structure an anticyclone. On Earth, we have much smaller versions, high-pressure systems that spin and generate weather patterns. But Jupiter's version operates on a completely different scale. The storm is not just wide, its roots go 200 miles deep into the planet's atmosphere. For comparison, the deepest ocean trench on Earth is less than 7 miles deep. This storm reaches 30 times deeper than that, extending into regions of Jupiter's atmosphere where the pressure is so extreme that nothing we have ever built could survive. And here is what makes the accelerating winds so strange and so important. In most storm systems, the outer edges slow down first as the system loses energy. That is basic physics. Energy dissipates from the outside in. So if the outer edges are speeding up, something is pushing energy into this storm from an outside source. The storm is not just sustaining itself, it is growing more intense. From where and through what mechanism? Those questions have no confirmed answer yet. But the further we go into this mystery, the stranger every layer becomes, because the wind speed is only the beginning of what cannot be explained. The acceleration of those outer winds means the boundary zone of the storm is becoming more energetic with every passing year. More energy at the edge means more intense interactions with everything around it. The storm is not simply maintaining itself at a dangerous level, it is becoming more dangerous, and the physics behind why that is happening remain, for now, unanswered. On Earth, storms die. That is a fact of nature here. A hurricane builds over warm ocean water, gains power, spirals tighter, and then makes landfall. The moment it hits solid ground, friction tears it apart. It loses its energy source almost instantly. It collapses within hours or days. Even the most powerful hurricanes in recorded history dissolved quickly once they reached land. Every major storm system on Earth follows this pattern. No matter how powerful, no matter how wide, the ground wins eventually. Jupiter does not have ground. This is not a small detail. It is the single most important thing to understand about why the Great Red Spot has survived for centuries while storms on Earth last days at most. Remove the ground, and you remove the mechanism that kills every storm we have ever studied on our own planet. Jupiter is a gas giant. From the very top of its clouds, all the way to its mysterious core, there is no solid surface, no land, no coastline, no friction waiting at the bottom of the atmosphere. A storm on Jupiter never makes landfall because there is no land to make. What exists instead is layer after layer of atmosphere, each one denser and stranger than the one above it. The top layers are made of ammonia and water ice crystals, forming those iconic colored clouds visible from Earth. Go deeper, and the pressure increases so dramatically that the hydrogen gas is compressed until it becomes liquid. Not like water is liquid, something far denser and far more extreme. Even deeper still, that liquid hydrogen transforms into something that does not exist naturally anywhere on Earth. Metallic hydrogen, a state of matter where hydrogen atoms are squeezed so tightly that electrons break free and move between atoms the way they do in copper wire. The hydrogen conducts electricity. It behaves like a metal, not a gas, and it extends for tens of thousands of miles into the planet's interior. At the very center, scientists believe there is a rocky core, though its exact nature remains uncertain. It may be solid, It may be a dense, semi-liquid mass. What is clear is that it is not anything a storm could crash into from above. So, the Great Red Spot has no natural ending point. It spins and feeds, and spins some more. Warm gases rise from below, cool gases fall from above. The storm draws them in, processes them, and keeps moving. The atmosphere itself becomes the fuel. With no land to stop it, and an endless atmosphere to feed from, the storm just continues. But no solid surface only explains why the storm does not get stopped. It does not explain what actively powers it. That mystery runs deeper than the surface. Literally, the atmosphere provides everything the storm needs to keep going. But no atmosphere is infinite in the energy it can offer. Something specific must be channeling that energy into the red spot in a sustained and consistent way. The lack of a solid surface removes the brake. It does not explain the accelerator, and finding that accelerator is what has researchers completely stumped. In 1665, a scientist named Giovanni Cassini pointed his telescope at Jupiter and noticed something unusual sitting in the planet's southern hemisphere. A dark, oval-shaped feature that appeared fixed in place relative to the cloud band surrounding it. He recorded it carefully, tracked it across multiple observations, and described it as a permanent spot. That observation is now believed to be the first recorded sighting of the Great Red Spot. If that identification is correct, the storm we are studying today has been continuously raging for close to 400 years, without pause, without interruption, without a single moment of rest. Let that settle in for a moment. 400 years ago, the Pilgrims had just landed in North America. Isaac Newton had not yet written his laws of motion. The first steam engine was still a century away from being invented. Shakespeare had only been dead for about 50 years. While human civilization was building cities, fighting wars, launching revolutions, developing modern medicine, and eventually sending rockets to the moon, this storm on Jupiter never stopped. Not for a day, not for an hour, not for a single second. It outlasted empires. It outlasted the entire arc of the Industrial Revolution. It outlasted the lifespan of every human being who has ever looked up at the night sky and observed it through a telescope. And it is still going right now, tonight, while you are listening to this. The sheer endurance of this thing is almost impossible to fully absorb. On Earth, weather systems are measured in days. Exceptionally, long-lasting hurricanes might persist for a few weeks if they stay over warm water and avoid land. A storm that survives for nearly 4 centuries is not just unusual, it belongs to an entirely different category of natural phenomenon. It is not a weather event. It is a permanent feature of a planet, and yet for most of those 400 years, we barely understood it. We saw it. We tracked its slow movement around Jupiter's southern hemisphere. We noted that its color changed, that its size shifted across decades, that it behaved differently at different times. But explaining what it was keeping it alive, what was making it the color it is, those questions remained completely open. They still are. Science has given us tools that Cassini could never have imagined. Space probes that have flown close enough to measure the storm's gravity, infrared telescopes that see heat invisible to the human eye, magnetic field sensors orbiting Jupiter right now, collecting data that takes hours to reach Earth. And after all of that technology, after all of that data, after all of that effort, the most honest summary researchers can offer is this. The storm is still here, it is still changing, and we do not fully understand why it exists the way it does. What comes next is where the real mystery begins to take shape. What comes next is where the established scientific consensus starts to fracture, and the real mystery begins to emerge in full. When Cassini first documented the spot in the 1600s, he had no framework for understanding what he was actually looking at. The very concept of a storm system on another planet had not been developed yet. Planetary science as a discipline did not exist. Cassini was working with the understanding of his era, which meant he was making his best interpretation of what a telescope could show him from Earth. He simply noted it as a permanent feature of Jupiter's appearance and moved on, remarkable in itself, but not yet understood. The word that shaped early thinking was surface. For much of the history of astronomy, scientists and observers assumed Jupiter had a solid surface hidden somewhere beneath its clouds. The idea that an entire planet could be made almost entirely of gas, with no rocky ground anywhere, was genuinely difficult to accept. It felt wrong on an intuitive level. Planets, in the experience of everyone on Earth, had ground. They had rock beneath them. They had something solid that defined them as places. So early astronomers assumed the red spot was some kind of fixed geographical feature sitting on or above that presumed solid surface. Perhaps an enormous mountain range rising above the cloud deck. Perhaps a massive volcano, like the shield volcanoes on Mars, but far larger. Perhaps a raised plateau of some kind, stable enough to have sat in the same general location for as long as anyone had been watching. These theories persisted because they made intuitive sense given what people believed about planets at the time. A permanent oval feature that stays in roughly the same latitude on the planet, that sounds like something anchored to a surface. It took advances in spectroscopy, the analysis of light to determine chemical composition, and eventually direct spacecraft exploration to reveal the truth. Jupiter has no surface to anchor anything to. The clouds go all the way down, transitioning through increasingly extreme states of matter until they reach a core that no storm could ever interact with from above. This realization shattered the early models completely. The red spot was not sitting on top of something. It was not anchored to anything. It was a free floating structure of rotating gas, somehow maintaining its shape and position and energy for centuries, with nothing to hold it in place and nothing to slow it down. That raised a question that still does not have a complete answer. What keeps the storm organized? What prevents it from simply expanding outward, losing its structure, and dissolving into the surrounding atmosphere the way smoke from a candle eventually disperses into a room? The storm knows what it is. Scientists are still trying to catch up. The storm is organized in a way that preserves its structure across centuries of continuous operation without any external anchor. Understanding what holds it together is one of the central challenges of planetary science today, and the clue that cracked open the question came not from a new theory, but from a prediction that turned out to be catastrophically wrong. By the early 2000s, the scientific consensus around the Great Red Spot was about as settled as planetary science ever gets. The storm was shrinking. The data was clear, consistent, and agreed upon by researchers around the world, working independently with different instruments and different methodologies. They all got the same answer. The storm was losing size, and the trend was accelerating. The models that planetary scientists built based on this data predicted something specific. If the shrinkage continued at its observed rate, the Great Red Spot would become roughly circular in shape around the year 2040. A circular storm is not the same as a disappearing storm, but it would represent a fundamental change in the storm's character. The iconic oval, stretching wider than Earth, would become something different, something smaller, something that might not even look like the same feature at all. Several prominent researchers went further. They suggested that after becoming circular, the storm might lose the ability to maintain itself entirely. The disappearance of the Great Red Spot, something that would have seemed absurd to astronomers a century earlier, began to be discussed as a genuine possibility within a human lifetime. News outlets picked it up, headlines appeared, scientists gave interviews. The narrative of the dying Great Red Spot became widely accepted, repeated in documentaries, and taught in introductory astronomy classes. Then, the Hubble Space Telescope gave scientists something that did not fit the narrative at all. When researchers sat down to analyze wind speed data collected over an extended period, they found that while the storm's physical size had indeed been shrinking exactly as measured, The winds at its outermost edge had been quietly accelerating, not dramatically, not in a way visible to casual observation, but consistently, year over year, in exactly the opposite direction from what a dying storm should produce. A storm losing energy should show slower winds. That is not a controversial claim. That is how energy conservation works in any rotating fluid system. Energy goes down, speed goes down. The math is straightforward. But the red spot's outer winds were speeding up. The energy was not going down. It was going up. The storm was not running out of fuel. Something was refueling it. The storm was not dying. It was compressing. Getting tighter, more concentrated, more intense, even as its footprint shrank, like a fire that appears to be getting smaller because it is burning hotter and consuming fuel faster. Smaller does not mean weaker. It might mean the opposite. Nobody predicted that. Not one of the models. Not one of the papers. The prediction failed completely, and it failed in the most interesting way possible by being wrong in the opposite direction. A prediction built on decades of careful measurement failed completely because the storm was not following the pattern anyone had mapped for it. The failure was not a minor discrepancy. It was a reversal, and reversal in science, when the data is solid, does not mean the question is answered. It means the question has just gotten far more interesting. The Hubble Space Telescope has been orbiting Earth since 1990 and has produced some of the most transformative scientific discoveries in history. Images of deep space, measurements of the expansion rate of the universe, studies of black holes, nebulae, and distant galaxies. But one of its less celebrated contributions is years of careful, patient wind speed measurements taken of Jupiter's Great Red Spot. The method scientists used was straightforward, but required enormous precision. Hubble's cameras captured high-resolution images of Jupiter at regular intervals. Within and around the Great Red Spot, there are always small cloud features, wisps, curls, and patches of distinct material that move with the wind. By tracking these features from one image to the next, like following specific leaves floating in a river to measure how fast the current is flowing, researchers could calculate precise wind speeds at different locations within the storm. It is painstaking work. Each feature has to be identified, tracked across frames, and measured carefully. Small errors in image alignment or timing can throw off the results. That is why it took years of data collection and careful analysis before the trend became clear enough to publish with confidence. What the researchers found when they examined data spanning roughly a decade was a pattern that surprised every member of the team that looked at it. The winds in the very innermost part of the storm had remained roughly stable. The core, as expected, was relatively calm compared to the outer ring. But the winds at the outermost boundary of the storm, the thin zone where the red spot's rotation meets the calmer atmosphere surrounding it, were moving faster than they had been years earlier. The increase measured at approximately 1.5 miles per hour per year. The team checked their methodology. They reanalyzed the data. They looked for sources of error that could explain away the result. The trend held. Amy Simon, a planetary scientist at NASA's Goddard Space Flight Center, who was part of the research team, described the discovery publicly as genuinely puzzling. The expectation based on the storm's visible shrinkage was that wind speeds across the board should be decreasing. Finding acceleration at the outer edge was not a minor discrepancy to be explained away. It demanded a new explanation. That explanation does not fully exist yet. Theories have been proposed, models have been adjusted, but a confirmed, definitive understanding of why those outer winds are accelerating while the rest of the storm shrinks, still unknown, and the question becomes significantly harder when you add the next discovery into the picture. The Hubble data revealed that the storm's behavior did not fit the existing models in any clean way. That is the kind of discovery that forces an entire field to stop. reassess its assumptions, and start asking fundamentally different questions. What those questions lead to in the upper atmosphere of Jupiter is something that makes the wind speed story look almost straightforward by comparison. Let us be direct about something. 1.5 miles per hour sounds completely trivial. Most people walk at around 3 miles per hour. A gentle autumn breeze moves at about that speed. If a weather report told you wind speeds had increased by 1.5 miles per hour overnight, you would not even notice the difference when you stepped outside. So, why are planetary scientists describing this as one of the most important and puzzling measurements they have taken of Jupiter in years? Context. In science, context changes everything. The Great Red Spot is not a local storm. It is not a regional weather system. It is a planetary-scale atmospheric engine that has been running continuously for centuries, generating winds that dwarf anything ever recorded on Earth, maintaining its structure across a volume of space that makes our entire planet look like a marble sitting next to a basketball. When a system operating at that scale shows a consistent year-over-year increase in energy output, even a small one, it means something is actively feeding it, not occasionally, not in bursts, continuously, at a rate that compounds over time. Energy does not appear from nowhere. The first law of thermodynamics is not a suggestion. If the outer winds are accelerating at 1.5 miles per hour every year, power is entering the system from somewhere, consistently. And that source has not been found. This is what makes it genuinely unexplainable, rather than just mysterious. It is not that scientists lack the intelligence or tools to study the problem. It is that the storm is behaving in a way that falls outside the boundaries of what current atmospheric physics predicts should happen. The models say the energy should be leaving. The measurements say it is arriving. Imagine a candle burning in a sealed room. Oxygen gets consumed. Eventually, the candle goes out. That is what models predicted for the red spot. Instead, the candle is burning brighter every year inside that same sealed room, and no one can find where the oxygen is coming from. Some researchers have proposed the storm is absorbing energy from smaller vortices around it, essentially consuming nearby storm systems and converting their energy into its own. Others point to deep atmospheric currents that may be channeling heat upward from the interior, invisible to our instruments, but powerful enough to make a difference. Still others focus on Jupiter's own internal heat. The planet radiates significantly more energy than it receives from the distant star it orbits, suggesting a powerful internal heat source that may be driving atmospheric behavior in ways not yet fully modeled. None of these explanations fully account for the consistent acceleration. None tie everything together into a complete picture, and the energy mystery does not stop at wind speed. It gets hotter from here, literally. The energy is there. It is measurable. It is consistent. And it has no confirmed source. That is what genuinely unexplainable looks like in real science. Not a ghost story, not speculation. A measurement that cannot be accounted for by the best models available. And the next measurement makes the energy mystery even harder to dismiss. Here is a detail about the Great Red Spot that does not get nearly enough attention, and it genuinely does not make intuitive sense when you first encounter it. The outer edge of the storm is a ring of destruction moving at 400 miles per hour. Pure, sustained violence on a scale that has no parallel in Earth's weather systems. A band of chaos wider than our entire planet, spinning without pause. But if you could somehow travel to the very center of that storm, the geometric heart of this cosmic hurricane, you would find something completely unexpected. It is calm, not peaceful in any absolute sense. Nothing on Jupiter qualifies as peaceful. But the winds at the center of the red spot move significantly slower than at the outer ring. Scientists have confirmed this structure repeatedly through Hubble's observations and through data returned by NASA's Juno spacecraft, which has been orbiting Jupiter since 2016 and has made multiple close passes over the storm. The storm has what researchers describe as a ring structure. The fastest winds concentrate along a band near the outer edge. Moving inward from that band, speeds decrease. The very core rotates more slowly than the surrounding ring. This is counterintuitive if you picture a storm, like a spinning top, fastest at the outside. The reality is more complex and more interesting. On Earth, the structure of a hurricane offers a partial comparison. The most violent part of a hurricane is the eye wall, a tight ring of intense thunderstorms immediately surrounding the calm eye at the center. You can fly a plane from the calm eye into the eye wall and experience an almost instant transition from smooth air to extreme turbulence. The red spot operates on a similar principle, but at a scale that makes terrestrial hurricanes look like minor weather events. What this structure tells researchers is that the storm is not randomly churning. It has organization. It has a specific architecture that has been maintained across centuries of continuous operation. The outer ring serves one function. The inner region serves another. The boundary between the storm and the surrounding atmosphere is where the energy peaks. If new energy is entering the system and pushing those outer winds faster, why is it not also affecting the center? Why is the boundary zone accelerating while the core remains relatively stable? What mechanism concentrates the new energy specifically at the ring and leaves the core relatively undisturbed? The structure is holding together in a way that current models struggle to fully replicate. And 200 miles below the cloud tops, in regions no spacecraft has ever directly sampled, something is maintaining all of it. Something we have never seen. The organized, layered structure of the Great Red Spot, with its calm core and its violent outer ring, suggests a system that knows something about maintaining itself that current science does not fully understand. It has been holding that structure for close to 400 years. Whatever principle governs it, it has proven more durable than every prediction made about its future. And underneath all of that structure, deeper than any instrument has ever reached, something is providing the foundation for it all. Most visualizations of the Great Red Spot show it from above, a swirling oval of red and orange, sitting on top of Jupiter's cloud deck, drifting slowly through the planet's southern hemisphere. Photographs, illustrations, documentary footage, all of them present the storm as a surface feature, something sitting on top of the planet, like a sticker placed on the outside of a ball. That image is deeply, fundamentally misleading. When NASA's Juno spacecraft flew close enough to take detailed gravity measurements around the Great Red Spot, the data revealed something that researchers had theorized but never directly confirmed. The storm's structure does not stop at the cloud tops. Its roots extend approximately 200 miles downward into Jupiter's atmosphere, 200 miles down into the planet itself. For perspective, consider Earth's geography. The average depth of the Atlantic Ocean is roughly 2 miles. The Mariana Trench, the deepest point on the entire surface of Earth, sits less than 7 miles below the ocean surface. The roots of the Great Red Spot extend 30 times deeper than the deepest point on our planet, purely in their vertical dimension, before you even account for the storm's horizontal width. This changes everything about how the storm has to be understood. A weather system that extends 200 miles into an atmosphere is not a surface phenomenon at all. It is a massive three-dimensional structure penetrating deep into regions of Jupiter's atmosphere, where the conditions are extreme in ways that make the cloud tops look gentle by comparison. At depths of 200 miles into Jupiter's atmosphere, the pressure is crushing. Temperatures are brutally high. The gases behave in ways that have no precise parallel in our everyday experience. Hydrogen at those depths is no longer the invisible, lightweight gas we think of from chemistry class. It is compressed into states that blur the line between gas and liquid in ways that our models are still working to fully characterize. The fact that the red spot extends this deep means that whatever is fueling it may be coming from below, from those deep atmospheric layers that Juno is only beginning to map with any precision. Layers where we cannot see directly, where our instruments have never reached, where the physics becomes significantly more uncertain than at the surface. Scientists describe the red spot using an iceberg analogy. What we observe when we look at Jupiter is only the visible tip of a structure that extends far out of sight. In this case, the hidden part stretches into a region we have never directly sampled, and that may be where the real power source lives. What comes next takes the temperature story to a level that should genuinely not be possible. The iceberg analogy is worth sitting with. The storm's visible surface is dramatic enough to capture the imagination of anyone who looks at Jupiter through a telescope. But the hidden portion, extending into depths no probe has survived, is where the real story may be written. And the heat that those depths are somehow generating in the atmosphere above the storm is the next chapter of a mystery that has no clean ending in sight. Picture yourself standing 1 mile directly above a massive fire, not beside it, not inside it, 1 full mile above it, in open air. You would feel warmth if the fire were large enough, but the further you get from any heat source, the cooler the surrounding air becomes. Heat rises, but it also spreads outward and loses intensity as it travels. Temperatures in Earth's atmosphere drop consistently with altitude. That is why mountain peaks are cold and why the upper atmosphere is colder still. This principle is not exclusive to Earth. It applies everywhere. It is basic physics, and basic physics does not have exceptions, except that in Jupiter's upper atmosphere, directly above the Great Red Spot, something appears to be violating it. In 2021, a research team used ground-based infrared telescopes to map the temperature of Jupiter's upper atmosphere in unprecedented detail. They built a temperature map of the entire planet's upper atmospheric layer, region by region, looking for patterns and anomalies. The results, which were published and peer-reviewed, showed something that no existing model had predicted and no researcher had expected to find. The highest temperatures ever recorded in Jupiter's atmosphere were concentrated directly above the Great Red Spot, not inside the storm. Not at the storm's cloud tops. In the upper atmosphere sitting above the storm, well above the visible cloud layer, at an altitude where temperatures in other parts of Jupiter's upper atmosphere are measured in hundreds of degrees below zero. The temperature recorded above the red spot reached approximately 2,400 degrees Fahrenheit. That number needs a comparison to land properly. Lava pouring from a volcano on Earth reaches temperatures between roughly 1,300 and 2,200 degrees Fahrenheit. 2,400 degrees is hotter than that. It is hot enough to vaporize certain metals, and it is sitting in the upper atmosphere of a gas giant, floating above a storm cloud, in a region that should by every physical principle be cold. Jupiter is far from the star it orbits. Its upper atmosphere, in regions away from the poles, normally sits at around negative 230 degrees Fahrenheit. The contrast between that baseline temperature and the 2,400 degrees found directly above the red spot is not a small discrepancy to be hand-waved away. It is a difference of over 2,600 degrees between what exists and what should exist. Something is heating that region of the atmosphere with enormous intensity, specifically and precisely above this one storm. The question of what that something is does not yet have a confirmed answer, but there is a theory, and the theory itself raises more questions. 2,400 degrees of heat sitting in the upper atmosphere above one specific storm, while the atmosphere everywhere else remains hundreds of degrees below zero. It should not be there. It has no confirmed explanation, and the theory that tries to account for it, while scientifically reasonable, has not been proven by direct measurement. Something is heating that part of Jupiter's sky, and whatever it is powerful enough to outperform lava. The leading theory for the superheating above the Great Red Spot involves two types of waves that travel through Jupiter's atmosphere: acoustic waves and gravity waves. Before going further, one important clarification. Gravity waves in this context are not the same as gravitational waves. those famous ripples in space-time detected by instruments designed to sense disturbances from colliding black holes. Gravity waves, in the context of atmospheric science, are something entirely different. They are waves that move through a fluid, in this case, a gas atmosphere driven by buoyancy and the force of gravity acting on air masses of different densities. When a dense blob of air gets pushed upward into a less dense region, gravity pulls it back down. It overshoots, bounces back up, overshoots again, and the oscillation creates a wave. Anyone who has seen rippling cloud formations downwind of a mountain range has seen the visual signature of gravity waves in Earth's atmosphere. The theory connecting these waves to the superheating works like this. The Great Red Spot is an enormous, continuously churning storm system. That churning generates massive amounts of turbulence, which in turn produces both acoustic waves, essentially pressure waves similar to sound, and gravity waves. These waves do not just dissipate locally, they travel upward through Jupiter's atmosphere, carrying energy away from the storm and into the layers above. As those waves rise into thinner and thinner atmospheric layers, something changes. In denser air lower down, the waves travel relatively easily without expending much energy. But as the atmosphere thins out at higher altitudes, the waves slow down, steepen, and eventually break. When they break, all the energy they were carrying releases at once, as heat. Think of ocean waves approaching a beach. In deep water, waves travel enormous distances without losing much energy, but as they reach the shallowing water near shore, they slow down, their energy concentrates, and they break with a crash that releases that stored energy as turbulence and foam. The upper atmosphere above the red spot may be functioning as the beach in this analogy. The waves generated by the storm travel upward and crash into the upper atmospheric layer, depositing energy as heat. This is a scientifically plausible mechanism. It is consistent with some of the observed data, but it has not been directly proven. Scientists do not yet have direct measurements of these waves traveling from the storm through Jupiter's atmosphere to the upper layers where the heat is found. The connection between wave generation at the storm and heat deposition above it is inferred from the spatial correlation, not observed from direct measurement of the wave pathway, which means 2,400 degrees of unexplained atmospheric heat remains, technically, unexplained by direct evidence. And the next mystery does not involve heat at all, it involves color. The wave theory is plausible. It is consistent. It is the best current explanation available. But plausible and consistent are not the same as proven. The gap between a theory that makes sense and a theory backed by direct measurement is exactly where this mystery currently sits, and the color of the storm, which also lacks a confirmed explanation, makes that gap feel even wider. The Great Red Spot is red. That is in the name. It is perhaps the single most recognizable visual feature in our entire solar system. The first thing anyone notices when they see a photograph of Jupiter is that swirling oval of red and orange sitting in the southern hemisphere like a permanent bruise on the planet's face. After 400 years of observation and decades of direct spacecraft data, including multiple close passes by instruments specifically designed to analyze Jupiter's chemistry, no one can fully and definitively explain why it is that color. This is genuinely strange when you sit with it. The storm's color is not subtle. It is not a faint tint that requires sensitive instruments to detect. It is a vivid, distinctive shade, ranging from pale salmon on quieter days to deep brick red during more intense periods. Something specific is producing that color. Some chemical, some reaction, some atmospheric process unique to that storm is creating the hue, and determining exactly what that something is has proven surprisingly difficult. Several theories have been proposed and studied over the decades. One early candidate was phosphorus. Certain phosphorus compounds have reddish colors, and phosphorus-containing molecules exist in Jupiter's deep atmosphere. If upward currents within the storm were lifting these compounds from lower depths into the visible cloud layer, they could theoretically contribute to the color. The theory was plausible. It was not confirmed. Another candidate was sulfur. Sulfur compounds can produce a range of colors from yellow to deep red, depending on their specific form and the conditions they exist in. Jupiter's atmosphere contains sulfur-bearing molecules, but again, the specific connection between those molecules and the exact appearance of the red spot was never nailed down with certainty. More recently, researchers focused on the storm's unusual altitude. The red spot sits slightly higher than the surrounding cloud deck, putting it in more direct contact with radiation from the star the planet orbits. Laboratory studies attempted to simulate what happens when simple molecules present in Jupiter's upper atmosphere. Things like acetylene and ammonia are exposed to ultraviolet radiation over extended periods. The results were interesting. The irradiated mixtures produced reddish-brown compounds. The colors were in the right general range. But when researchers compared these laboratory results to the actual observed spectrum of the red spot, the match was close but not exact. The real storm produces a specific shade that the laboratory approximations do not fully reproduce. Something about the conditions inside the actual storm, the specific mix of chemicals, the temperature, the pressure variations, the way radiation interacts with the churning interior produces a result that controlled laboratory conditions cannot perfectly replicate. The color of the most famous storm in the solar system is still, officially, an educated guess supported by evidence but not confirmed by it. 400 years, multiple spacecraft, dedicated laboratory experiments, and the color of the most famous storm in the solar system is still a theory, not a fact. Each partial explanation reveals another gap. Each gap points toward the hidden chemistry happening inside the storm at depths we have never directly sampled. The answer may be in a layer that sits just below the reach of the only probe we ever sent into Jupiter's atmosphere, approximately 30 miles below the visible cloud tops of Jupiter, hidden from direct observation by the thick cloud layers above it. Scientists believe there is a distinct chemical layer composed primarily of ammonium hydrosulfide. It forms when ammonia gas and hydrogen sulfide gas combine under the pressure and temperature conditions that exist at that depth in Jupiter's atmosphere. This layer has never been directly sampled. No probe has ever reached it and returned data. Scientists know it almost certainly exists based on the known chemistry of Jupiter's atmospheric components and by working backward from what spacecraft have been able to measure in the layers above. But the direct evidence for what is actually happening down there is essentially zero. Here is why it matters enormously for the red spot color mystery and for the broader question of what is happening inside the storm. Some researchers believe that this hidden chemical layer, specifically in the region directly beneath the Great Red Spot, may be undergoing reactions driven by cosmic rays or by ultraviolet radiation that penetrates partially through the cloud layers above. Cosmic rays are high-energy particles that stream through space from distant sources and can penetrate deep into planetary atmospheres. Ultraviolet radiation from the distant star the planet orbits also reaches into Jupiter's atmosphere to varying depths depending on cloud thickness. If those energy inputs are triggering chemical reactions in the ammonium hydrosulfide layer, the products of those reactions might be getting lifted upward by the red spot's powerful internal circulation currents. The storm's structure involves gas rising from deeper layers and falling from higher layers continuously. If reddish chemical products form below and get carried upward to the visible cloud layer, they could contribute to the storm's distinctive color. This theory has some observational support. The reddest, most intensely colored regions of the Great Red Spot tend to correspond to areas where upward motion within the storm is strongest. The correlation is not perfect, but it exists. The problem is that the one probe we sent deep into Jupiter's atmosphere, the Galileo entry probe in 1995, survived for roughly an hour before being destroyed by increasing pressure and temperature. It reached about 100 miles down before failing. The ammonium hydrosulfide layer sits around 30 miles down, which suggests it should have been within reach. But the probe was not instrumented specifically to study this layer in depth, and the data it returned raised as many questions as it answered. The most direct answers about what is happening in Jupiter's hidden chemistry sit at depths we have never successfully sampled, inside a storm whose color we still cannot fully explain. And the color mystery is actually one of the more contained puzzles. The next one involves the entire planet changing its appearance, and it happens on a schedule nobody fully predicted. The hidden chemistry of Jupiter's atmosphere may hold the answer to the color question and potentially to several others. But reaching it requires surviving conditions that destroyed our best probe within an hour. Until we build something capable of going deeper and lasting longer, the chemical layer beneath the red spot will remain one of the most scientifically important unsampled environments in the solar system. And the mystery extends beyond chemistry into the visible structure of the entire planet. Jupiter's surface has one of the most recognizable appearances in the solar system. Alternating bands of dark brown belts and lighter cream-colored zones wrap around the planet in parallel stripes, running east to west in a pattern that has been visible to telescope users for centuries. It is orderly. It is predictable. It looks almost painted on, but every few years, something happens that upends that appearance in a way scientists are still working to fully understand. The stripes change, not slightly, not in a way that requires sensitive instruments to detect. The changes can be dramatic enough to see through a reasonably equipped amateur telescope from Earth. Regions that were dark brown become noticeably lighter. Lighter zones darken. The overall banding pattern reorganizes. In infrared imaging, which detects heat rather than visible light, the reversal is even more dramatic. Bands that appear pale in normal visible light show up as dark in infrared, and the bands that looked dark become bright. This switching has been documented multiple times across decades of observation. One of the most striking examples occurred in 2010, when Jupiter's south equatorial belt, one of the most prominent and consistently dark features on the planet, faded almost entirely to white over the course of weeks. Astronomers noticed immediately. The change was dramatic enough to generate news coverage and significant attention from the amateur astronomy community. About a year later, the belt returned, reasserting its familiar dark brown color and resuming its normal appearance. Scientists determined that what happened in 2010 was not the belt's circulation disappearing. The storm activity within the belt was still occurring underneath. What happened was that a layer of white ammonia ice clouds formed on top of the belt, hiding it from view. The underlying dynamics continued, invisible beneath that bright white covering. But that explanation only describes the mechanism of one specific event. The deeper question, why do these cloud coverings form when they do? Why the pattern can reorganize so dramatically? Why the timing follows some kind of cycle that nobody predicted in advance? Remains much less settled. The most promising current explanation connects the stripe changes to something happening far below the cloud tops, in the deep interior of the planet. Something that involves forces most people have never heard of, and that Jupiter appears to express in ways no other planet in the solar system has shown us clearly. The stripe reversals happen on a timescale of years, driven by processes happening tens of thousands of miles below the visible surface. The fact that we can now connect surface observations to deep interior physics at all is remarkable on its own. The fact that the connection is still not fully proven by direct measurement is a reminder of how much remains to be understood about this planet. The key to filling in that gap may lie in a feature of Jupiter's interior that almost nobody outside of planetary science has ever heard of. To understand what might be driving the stripe reversals, you have to understand something about Jupiter's interior that was only mapped with real confidence in the past decade, thanks to data returned by the Juno spacecraft. Deep inside Jupiter, At depths far below anything any probe has ever reached, there is a layer of metallic hydrogen. The phrase sounds like something invented for a movie, but metallic hydrogen is a real state of matter, one that exists nowhere naturally on Earth, but that forms under the crushing pressures present inside gas giants. At those pressures, measured in millions of times greater than the atmospheric pressure on Earth's surface, hydrogen atoms are compressed so tightly together that their outer electrons are no longer bound to individual atoms. The electrons become free to move between atoms, exactly as electrons move through copper wire or iron. This means that deep inside Jupiter, there is a vast, rotating sphere of electrically conducting fluid. And electrically conducting fluid in motion generates a magnetic field. Jupiter's magnetic field is the strongest of any planet in our solar system, approximately 20,000 times stronger than Earth's. Its influence extends millions of miles into space, creating a magnetosphere large enough to engulf the orbit of Saturn if placed at the center of the solar system. That magnetic field is not static. It shifts, it fluctuates, and it contains internal structures that move over time. When Juno began mapping Jupiter's magnetic field in fine detail, it detected something that had been theorized but never directly observed: rhythmic oscillations in the field's internal structure, wave-like fluctuations, regular and repeating, moving through the metallic hydrogen layer deep inside the planet. The technical name for these motions is torsional oscillations. Picture the interior of Jupiter as a series of fluid layers stacked concentrically, each rotating at a slightly different speed. The magnetic field threads through all of them, like invisible wire running through a coil. As the conditions inside the planet change over time, the field fluctuates, and those fluctuations push and pull on the conducting fluid in each layer. The fluid responds by developing wave-like motions that travel outward from the deep interior toward the atmosphere. When the research team compared the timing of these oscillations to the documented timing of the stripe reversals visible on Jupiter's surface, they found something that made the connection hard to dismiss. The periods matched. The rhythm of the deep magnetic waves appeared to align with the rhythm of the surface color changes. What happens in the invisible interior of the planet seems to be directly controlling what billions of kilometers away we see on the outside. But there is one specific piece of this magnetic system that almost nobody discusses, and it might be the most important indicator of where things are heading. The rhythm of the interior may be the rhythm of everything visible on the surface. Torsional oscillations are not something you can see or touch. They are abstract patterns in the behavior of electrically conducting fluid deep inside a gas giant. But their fingerprints appear to show up in the banding pattern of a planet seen from hundreds of millions of miles away. And one specific magnetic feature connected to these oscillations is doing something right now that researchers are watching very carefully. When Juno completed its first detailed magnetic field map of Jupiter, planetary scientists expected something broadly similar to what they found with Earth: a relatively organized magnetic field with clear poles and a roughly dipole structure, perhaps a bit lopsided, but fundamentally familiar in shape. What they actually found was significantly more complex and far more interesting than that. Jupiter's magnetic field is patchy, lumpy. It has concentrated regions of intense magnetic strength distributed unevenly across the planet, some near the poles and some in unexpected locations. The overall structure does not resemble a simple bar magnet the way Earth's field roughly does. It looks more like a magnetic field generated by multiple sources interacting with each other in complicated ways deep inside the planet. Among these concentrated magnetic patches, there is one in Jupiter's southern hemisphere that researchers have named the Great Blue Spot. It is not a visible feature. You cannot see it through a telescope. It produces no light and creates no observable cloud pattern on its own. It is a region of unusually intense magnetic field buried within Jupiter's atmosphere, detectable only through the kind of magnetic measurements Juno was specifically designed to make. and named as a southern hemisphere companion to the Great Red Spot in the same latitude band. Here is what makes it critical to the larger mystery. The Great Blue Spot is moving. It drifts slowly westward around Jupiter, carried by the deep atmospheric currents flowing beneath the visible cloud layer. Researchers have been tracking its position across multiple Juno orbits, building up enough data to measure not just where it is, but how fast it is moving and whether that speed is changing. It is decelerating. Slowly but consistently, the Great Blue Spot's westward drift is slowing down. And according to the scientists analyzing the data, this deceleration is not random. It suggests that the torsional oscillations deep inside Jupiter are entering a transition, a shift in the deep magnetic rhythm that has been driving the spot's movement. If that transition happens, and if the torsional oscillations do enter a new phase, as the deceleration suggests, the stripe reversal cycle at the surface may be about to change as well. The blue spot's behavior might be serving as an early warning signal, a preview of the next round of visible changes that observers will see on Jupiter's surface, which would mean that for the first time, we might be able to look at a magnetic anomaly in Jupiter's interior and say, with some confidence, what is coming next. That would be extraordinary, and it still would not explain why any of this is happening in the first place. The Great Blue Spot is the interior made visible through magnetic measurement. Its slow drift and its deceleration are reading like a ticker tape from Jupiter's deep interior, spelling out something about the next phase of the planet's magnetic and atmospheric cycle. Scientists are watching it carefully. What it predicts may reshape how the entire planet looks from the outside, and understanding how that reshaping happens requires tracing the pathway from the invisible interior to the visible surface in detail. Connecting the oscillations deep in Jupiter's interior to the visible stripe reversals on its surface requires tracing a chain of causes and effects across tens of thousands of miles of atmosphere. Scientists are still assembling that chain, but the current model, in its simplified form, offers the clearest picture we have of how the inside of a planet controls the weather on its outside. Here is how the thinking goes. Deep inside Jupiter, the torsional oscillations create slow, rhythmic movements in the metallic hydrogen layer. These movements are like a vast, sluggish stirring happening in an enormous container of electrically conducting fluid. The stirring is not dramatic. It happens on timescales of years, not seconds. But it affects something crucial: the currents that transport heat from the planet's deep interior upward toward the atmosphere. Jupiter is not just a passive ball of gas sitting in space. It generates its own internal heat. The planet radiates more energy into space than it receives from the distant star it orbits, which means something inside Jupiter is producing heat continuously. That internal heat has to get from the interior to the outside somehow. The mechanism is convection. Hot material rises, cooler material sinks. Heat gets transported upward in a slow churning process. When the torsional oscillations alter the pattern of this internal stirring, they change how heat is transported. More heat arriving at the base of the atmosphere in one region means more vigorous rising air in that region. Less heat in another region means less vigorous rising there. And the balance between rising and sinking air in Jupiter's atmosphere is exactly what determines the structure of the belts and zones. Belts are regions where gas is descending. Zones are where gas rises. The descending regions tend to have thinner clouds and appear darker. The rising regions produce thicker clouds that appear lighter. Flip the balance between rising and sinking, and you flip the appearance. What was a dark belt becomes a bright zone. What was a light zone becomes a dark belt. From Earth or from an orbiting telescope, what this looks like is the stripe reversal that has puzzled observers for decades. The surface is not changing its fundamental structure. The deep interior is rearranging the heat transport, and the surface responds. This model is the most complete framework currently available, but it has important gaps. The torsional oscillations themselves are inferred from magnetic field measurements, not directly observed as fluid motion. The exact pathway from deep oscillation to surface cloud reorganization passes through poorly understood intermediate layers, and the model has not yet been tested against a full stripe reversal event in real time with Juno in orbit and fully operational. The next reversal, whenever it comes, may finally give scientists the data they need to either confirm this model or send it back for revision. The model is compelling, the gaps are real, and the test of whether the model is correct may come sooner than expected. If the Great Blue Spot's deceleration is the warning signal researchers think it is, the next stripe reversal event, observed in real time with Juno still operational, could either confirm the framework or force another complete reassessment. Either outcome would be one of the most significant findings in planetary science in decades. The cloud tops of Jupiter are the planet's face. Colourful, dynamic, constantly in motion, they are what photographers capture, what documentaries show, what most people picture when they think of the largest planet in the solar system. But those clouds, as dramatic as they look, are a relatively thin layer sitting on top of a vastly larger and stranger interior. Below the uppermost ammonia ice clouds, there are additional distinct cloud layers. Water ice clouds exist deeper in the atmosphere, at depths where temperatures allow water to freeze into crystals. Below those, ammonia and water combine into solution droplets, forming a third cloud layer with different properties. Each layer exists at a specific altitude where the temperature and pressure allow particular materials to condense out of the surrounding gas. These layers are not purely theoretical. The Galileo probe, which descended into Jupiter's atmosphere in 1995, detected signatures of multiple distinct cloud layers during its descent, though the data was incomplete and the probe did not survive long enough to fully characterize all of them. Below all of the cloud layers, the atmosphere transitions from gas into something in between gas and liquid, then into liquid, and then eventually into that metallic hydrogen state described in the chapter about Jupiter's magnetic field. Each transition happens over enormous depth ranges, driven by steadily increasing pressure and temperature. No spacecraft has survived a trip through all of these layers. The Galileo probe, the only one ever deliberately sent into Jupiter's atmosphere, lasted approximately 1 hour before the combination of temperature and pressure destroyed it. During that hour, it sampled the upper atmosphere and returned data that surprised scientists in several ways. The amount of water detected was lower than pre-mission predictions. The winds were stronger at depth than models had expected. The structure of the atmosphere was more complex than the simplified models suggested. Every piece of data that probe returned before it was crushed challenged assumptions that researchers had held with reasonable confidence. Every time we get a direct measurement from inside Jupiter, something surprises us, which means that everything we believe we understand about what is happening below the cloud tops is built on a very small foundation of actual data, supplemented by modeling and inference. The Great Red Spot's roots extend 200 miles down. The deepest direct atmospheric measurement we have from Jupiter reached only about 100 miles. The storm goes deeper than our deepest observation. The mystery extends further than our instruments have ever reached. Something exists down there, something connected to the storm above, to the heat anomaly above that, to the magnetic oscillations deeper still. Understanding it completely will require technology we have not yet built. Every direct measurement we have ever taken from inside Jupiter surprised us. That pattern does not inspire confidence in the completeness of our models built from the outside. The Great Red Spot extends into regions we have never sampled. Whatever is down there, connected to the storm above and to the heat anomaly and the magnetic oscillations and all the other mysteries layered on top of each other, is waiting to be found by instruments we have not yet built. Meanwhile, on the surface, the storm is doing something that nobody predicted. One of the most directly confirmed facts about the Great Red Spot is that it feeds on smaller storm systems that drift into its vicinity. This is not an inference or a theory extrapolated from partial data. This is something scientists have watched happen in real time through Hubble observations, documented with high-resolution imagery, and studied in enough detail to understand the basic mechanics of how it works. Jupiter's atmosphere is full of smaller vortices, oval-shaped storm systems, some of them, the size of major continents on Earth, spin through the planet's cloud bands alongside the belts and zones. These smaller storms form, persist for years or decades, and eventually dissipate. Most of them are unremarkable in the context of the overall planetary weather system. They form, they spin, they fade. But when one of these smaller vortices drifts into the gravitational and fluid dynamical influence zone of the Great Red Spot, something that looks almost biological happens. The smaller storm is drawn into the outer circulation of the red spot. It begins to stretch, its structure distorted by the difference in wind speeds between its leading and trailing edges as it gets pulled in. It breaks apart. Its cloud material and its energy get absorbed into the larger system. The red spot consumes it. This process has been observed multiple times. In some cases, the absorption of a smaller storm causes temporary disruptions in the red spot structure. Observers have documented moments when the storm's boundary becomes turbulent and irregular following the absorption of a nearby vortex, before the system settles back into its regular rotation pattern. The red spot digests what it has consumed and returns to its characteristic structure. This feeding behavior is almost certainly one of the mechanisms contributing to the storm's remarkable longevity. By absorbing the energy and material of smaller systems, the red spot supplements whatever other power sources are sustaining it. It is not entirely self-contained. It recruits from the planet around it. But this creates a question that complicates the acceleration narrative in an important way. If the red spot is consuming surrounding storms, those smaller systems are finite. There is a limit to how many are available at any given time. A system that feeds on smaller systems is also reducing its own future food supply. And as the red spot has shrunk in size, its influence zone has also shrunk, potentially making it harder to capture storms that form at greater distances. Is the storm's current wind acceleration partly driven by an increasingly concentrated feeding process? And if the supply of nearby smaller vortices decreases over time, will the acceleration eventually stall? These questions do not yet have confirmed answers. But the edges of the storm are already showing signs that something is changing in how it interacts with its surroundings. The red spot has been the dominant predator of Jupiter's southern hemisphere weather system for centuries. But the neighborhood is changing as the storm shrinks and its feeding zone contracts. Whether the changes at the storm's edges are a sign of a new phase in its relationship with the surrounding atmosphere, or simply the natural turbulence of a very old storm boundary, is one more question that current data cannot fully settle. And the edges are doing something new. In 2019, observational reports began noting something new happening at the outer boundary of the Great Red Spot that had not been prominently documented in previous years. Small pieces of the storm were detaching from the edges and drifting away. The process got described in science media as flaking. The images that captured it were striking enough to circulate widely. This ancient, seemingly permanent storm, the one everyone had been debating the future of for years, suddenly looked like it was shedding material from its borders in wisps and curls that separated from the main structure and dissolved into the surrounding atmosphere within days. Scientists were careful to contextualize the observation. Flaking at the outer boundary was not, in their assessment, a clear sign of the storm's imminent collapse. The material being shed was coming from the outermost transition zone of the storm, the boundary layer between the red spot's organized rotation and the calmer atmospheric bands flowing past it on either side. That boundary zone is already the most turbulent and dynamically complex part of the entire storm system. The leading explanation connects the flaking to interactions between the storm and the atmospheric jets that flow past it. Jupiter's belt and zone structure means that parallel rivers of fast-moving gas stream past the red spot continuously, some moving in opposite directions relative to the storm's outer rotation. Where the storm's edge meets those flowing jets, the difference in velocities creates shear forces. Think of it as two rivers of different speeds running right next to each other, with turbulence forming at the interface. In fluid dynamics, these shear zones are unstable, and material can get torn away from the slower moving body and carried into the faster flow. At a planetary scale, that process produces the wisps and flakes observed breaking off from the storm's edge. Here is what makes this directly relevant to the wind acceleration discovery. If the outer winds are speeding up, the velocity difference between the storm's boundary and the surrounding atmospheric jets is increasing. More shear, more instability, more material potentially being torn away. This suggests that the flaking and the acceleration may be two symptoms of the same underlying process. Something that is concentrating the storm's energy inward may simultaneously be making its outer boundary more vulnerable to disruption. The storm may be pulling its power toward its core while the edges become less stable. If that model is correct, what we are watching in real time is the storm entering a new phase of its evolution. Not dying, reorganizing. And the reorganization has implications that nobody fully predicted. The flaking edges, the accelerating outer winds, and the shrinking total area all point toward a storm in active transition. Whether that transition leads somewhere new or somewhere final is the question that will define Jupiter observation over the coming decade. The models that predicted steady decay were wrong. Whatever comes next will likely be something equally unexpected. And the 2040 timeline, built on those same flawed models, deserves a much harder look. The 2040 timeline has been circulating in popular science coverage for years. It originates from a reasonable geometric extrapolation based on measured data, and it deserves to be examined carefully rather than accepted or dismissed outright. Here is what the data actually showed. Through the late 20th and early 21st centuries, the Great Red Spot was losing area at a measurable rate. Its north to south dimension was shrinking more rapidly than its east to west dimension, making the oval progressively less elongated. Mathematical extrapolation of that trend, assuming it continued at roughly the same rate, pointed toward a date when the storm's north-south and east-west dimensions would be approximately equal, producing a circular rather than oval storm. That date landed near 2040. Some scientists, and significantly more journalists, extended the extrapolation further. If the storm continues shrinking past that circular stage, it could eventually become too small to sustain itself and disappear entirely. This is where the death of the Great Red Spot headlines came from. The wind acceleration data fundamentally complicated this narrative. A storm that is losing area while simultaneously intensifying in wind speed is not following the straightforward decay trajectory that the 2040 prediction was built on. The prediction assumed that shrinkage in area corresponded to loss of energy and rotational speed. The measurements showed that was not happening. The storm was getting smaller in footprint, but not correspondingly weaker in intensity. There are several possible futures consistent with what we now know. The storm could continue shrinking until it reaches a critical minimum size, below which it cannot maintain its structure, then rapidly collapse. Or it could reach some equilibrium state, smaller than its historic size, but stable at that scale, sustained by whatever energy source has been accelerating its outer winds. Or the shrinkage rate could change, slow, or even reverse if conditions in the surrounding atmosphere shift. Current models cannot reliably distinguish between these possibilities. The storm's behavior over the next decade will be more informative than any prediction generated from data collected before the acceleration was discovered. What is genuinely uncertain is whether the 2040 date means anything at all given what we now know. It was built on an assumption that the storm's behavior would remain consistent with past trends. The past trends have already broken. The 2040 prediction was built on a trend that has already broken. The storm is not following the script. Its wind speeds are rising while its total area falls, which is precisely the combination that the original extrapolation never accounted for and could not have predicted. Whether the 2040 prediction retains any practical validity at all, given what we now know is genuinely uncertain among the researchers who study this most closely, scientists are watching, measuring, and carefully revising their models. The next decade of accumulated data will tell us whether that deadline means anything at all, or whether the storm has once again made the prediction look completely irrelevant. Even with all the uncertainty about what the red spot will do, the possibility of its eventual disappearance is real enough that researchers have thought seriously about what that would mean for Jupiter's atmosphere and what it would mean for science. The red spot has been a dominant organizing feature of Jupiter's southern hemisphere for nearly 4 centuries. Its presence shapes the atmospheric flow around it simply by existing. A storm that wide and that energetically intense deflects the belt and zone circulation that flows past it. It creates wakes, it captures nearby vortices, it imposes its rotation on the surrounding atmosphere for thousands of miles in every direction. Remove the red spot, and all of that influence disappears simultaneously. What fills the void is completely unpredictable from current models. The atmospheric jets that previously flowed past the storm on either side would continue, but without the deflection and disruption the red spot provided, they might reorganize into different patterns. New vortices would almost certainly develop in the region. How large they would grow, how long they would persist, whether any of them could eventually reach the scale or stability of the red spot is genuinely unknown. Some researchers speculate that the absence of the red spot might actually allow a new generation of large vortices to develop in the southern hemisphere. The red spot has been consuming nearby storm systems for centuries, reducing the population of large storms that could potentially become competitors. Without that predatory presence, smaller storms might grow larger, merge, and create new systems. The region might become more dynamically complex rather than simpler. For scientists, the disappearance of the red spot would be a uniquely valuable observational event. Watching a major region of Jupiter's atmosphere reorganize in real time, from the first moments after the storm collapses to the new equilibrium that eventually establishes itself, would provide data about gas giant atmospheric dynamics that no computer simulation could substitute for. Juno, if still operational, would be perfectly positioned to document the transition. For the rest of us, it would mean losing one of the most ancient observable features in the solar system, a storm that was already old when the first modern scientists were being born. A feature that generations of humans have pointed telescopes at, wondering what it was, how it worked, and how long it would last. It has outlasted every prediction about its death so far. But what comes next reveals just how strange the whole picture really is when you hold all the pieces together. The disappearance of the Great Red Spot, if it comes, will be one of the most scientifically valuable events ever observed in planetary science. It will also mark the end of something that has been part of Jupiter's identity for as long as humans have known the planet through telescopes. The storm has outlasted every prediction of its death so far. Whether it continues to do so, or whether we are watching the final centuries of a 400-year phenomenon, is a question that only time and continued observation can answer. And the real paradox is that even as it possibly fades, it is simultaneously doing something that defies easy explanation. Let us be precise about what makes the Great Red Spot genuinely unexplainable right now. Rather than simply mysterious or incompletely characterized, the core paradox is this: the storm is shrinking and intensifying at the same time. These two observations should not coexist. They point in opposite directions in terms of what they imply about the storm's energy state, and reconciling them within existing physical models is something researchers have not yet managed to do. When a storm loses size, it is losing the geographic extent over which it collects and processes energy. Smaller footprint means less atmosphere being processed, less material being cycled through the system, less surface area interacting with surrounding atmospheric flows. In standard models of rotating fluid systems, this corresponds to a decrease in total energy and consequently a decrease in wind speeds, particularly at the outer boundary where the system interfaces with the surrounding environment. The red spot is shrinking. That is confirmed by decades of measurement. Its area today is significantly smaller than it was a century ago. The trend in size is clearly downward, but its outer winds are accelerating. That is also confirmed by the Hubble wind speed analysis. More energy is present in the outer ring, not less. The boundary zone is moving faster with each passing year. How do you shrink and get stronger simultaneously? The figure skater analogy offers a partial answer. When a skater pulls their arms inward while spinning, they spin faster. The same angular momentum, concentrated into a smaller radius, produces higher rotational speed. If the red spot is undergoing a similar process, compressing its energy into a tighter structure, the shrinkage and the acceleration could be two aspects of the same physical process rather than contradictory observations. But the figure skater analogy has a critical limitation. A skater pulling in their arms is a closed system. No energy enters or leaves. The skater spins faster for a moment, then slows as friction from the ice acts over time. The skater does not spin faster and faster indefinitely, and a skater whose arms are being pulled in does not spontaneously generate more energy. The red spot has been operating for 400 years. Whatever is compressing it is doing so over an extraordinary timescale, without the system collapsing, and with the outer winds showing a trend of acceleration rather than a one-time adjustment. That does not describe a closed, conserving system. That describes a system receiving ongoing energy input. The source of that input remains unidentified, and that honest admission sits at the center of everything that makes this storm so genuinely remarkable. The paradox is real. The measurements are solid. The models are incomplete, and the storm continues operating in direct contradiction to what should happen according to the physics we have. That is not a problem with the physics. That is a signal that the physics, as applied to this specific system, is missing something. Finding what is missing may be the most important single task in planetary atmospheric science right now. Because whatever is missing here may also be missing from our understanding of planetary weather everywhere else in the universe. Science is most credible when it is clear about the difference between what is confirmed, what is theorized, and what is simply unknown. So here, plainly stated, is the list of things that remain genuinely unresolved about the Great Red Spot after centuries of observation and decades of direct spacecraft study. We do not know what energy source sustains the storm's 400-year operation. Deep atmospheric currents, absorption of smaller vortices, and Jupiter's internal heat are all candidates. None have been confirmed as the primary driver. The question remains open. We do not know why the outer winds are accelerating while the storm's total size shrinks. The paradox is real, reproducible in the data, and unresolved in the models. No published explanation has been accepted as complete by the broader research community. We do not know why the atmosphere, 2,400 degrees Fahrenheit above the storm, is so dramatically hotter than the surrounding upper atmosphere. Sound waves and gravity waves generated by the storm are the leading theory. Direct evidence connecting the wave generation to the heat deposition has not been established. We do not know definitively why the storm is red. Multiple theories exist. Laboratory experiments produce approximate matches. The exact chemistry happening inside the actual storm has never been directly sampled at the relevant depths. We do not know what the storm will do over the coming decades. Will it continue shrinking? Stabilize at a smaller size? Accelerate its wind speed further? Collapse suddenly? No current model reliably predicts the outcome. We do not know what is happening 200 miles below the cloud tops where the storm's roots reach. The physics there are inferred from gravity measurements, not from direct observation. No instrument has ever survived that depth. We do not know whether the stripe reversal cycle is fully explained by the magnetic torsional oscillations Juno detected, or whether there are additional mechanisms at work that have not yet been identified. This list is not a criticism of the researchers who study Jupiter. They are doing extraordinary work with extraordinary tools in extraordinarily difficult conditions. Every piece of knowledge on this list was harder to obtain than almost any scientific measurement taken on Earth. The fact that the list of unknowns is still this long is not a failure of science. It is a testimony to how genuinely complex Jupiter is and how much the universe has left to show us even in our own cosmic backyard. The list of unknowns is not shrinking quickly. Each new observation tends to raise as many questions as it answers. That is the nature of being at the frontier of knowledge. The storm has been studied for longer than most scientific disciplines have existed, and it is still generating new mysteries. The next spacecraft, the next telescope generation, the next decade of Juno data, any of these could change the picture dramatically, or they could deepen it. Either way, the story of the Great Red Spot is nowhere near its final chapter. Jupiter is, on average, roughly 440 million miles from Earth. Its storms are not going to affect your weather forecast tomorrow. The Great Red Spot is not coming here. By any practical measure, this seems like a distant problem fascinating to think about, but ultimately someone else's concern. That framing misses something important. The physics that governs Jupiter's atmosphere is the same physics that governs Earth's. Fluid dynamics, heat transport, the relationship between magnetic fields and conducting fluids, the way rotating systems store and release energy, these are not Jupiter-specific principles. They are universal. When scientists discover that their models cannot fully explain the behavior of the largest storm in the solar system, they are simultaneously discovering that those same models have gaps that apply everywhere those models are used. Climate models that project Earth's future weather and temperature patterns are built on the same atmospheric physics used to model Jupiter. Every gap in understanding revealed by the red spot mystery is a gap that also exists, in some form, in the tools used to understand our own planet's atmosphere. Every insight gained from studying the red spot is a potential improvement to those tools. This is not abstract. Improvements to atmospheric physics models translate directly into better climate projections. Better climate projections translate into better policy decisions about energy, infrastructure, and resource management. The mysteries of Jupiter are connected by the chain of scientific understanding to questions about the future of life on Earth. There is also a broader and harder question sitting underneath all of this. We have been studying Jupiter for centuries. We have sent multiple spacecraft to orbit it, probe it, and fly through its neighborhood. We have dedicated decades of telescope time to it. We have applied the best atmospheric physics, computational modeling, and measurement technology available to the question of how this planet works. And the Great Red Spot, the most prominent feature on the most prominent planet in our solar system, is still producing observations that our best models cannot fully explain, still doing things that nobody predicted, still generating questions faster than answers. What does that tell us about our understanding of the universe beyond what we can see from here? If a storm on a neighboring planet in our own solar system is still full of mysteries, how much remains unknown beyond that? How many assumptions built into our models of stars, galaxies, and cosmic evolution are as incomplete as our models of Jupiter's weather turned out to be? Something unexplainable is happening on Jupiter. The most important word in that sentence is unexplainable. Not yet explained, not beyond explanation, but currently sitting outside the boundaries of what our best science can fully account for. That is not frightening. That is an invitation. Every unexplained observation in science is a door. The storm has been knocking for 400 years. We are finally starting to listen. We are listening more carefully now than ever before. Juno is orbiting Jupiter right now, sending back data every hour. Ground-based telescopes are watching. Computer models are being revised. The questions the red spot is asking are being treated with the seriousness they deserve. The storm has been knocking for 400 years. We are finally starting to build instruments sensitive enough to hear what it is actually saying.